Okay, so let's start. Uh, if you recall, we were discussing ways and means of biasing a transistor using constant current sources, and we have discussed two topologies till now. And if I take you back to the previous lectures, so these were the four possible combinations that we were looking at, right? So the current source can be either connected at the drain or connected at the source, which essentially means that we kind of have two terminals from which we can observe if the transistor is able to provide adequate amount of current to balance out the current source while keeping it in saturation, right? So essentially we had two terminals to apply current, and we also have two terminals to tweak the gate to source voltage, because ultimately gate to source voltage has to be tweaked automatically. You cannot have two independent ways of, you cannot have two independent sources which are independently trying to bias a transistor. Then it causes a problem. So essentially, either you should have one particular voltage source which biases VGS, or a current source, right, which tells the transistor to auto-adjust its VGS with respect to whatever is needed to feed in the current. So in that vein, we saw that, I mean, we didn't see all the architectures, but at least we can appreciate that the current source can be connected either at the drain or at the source, which means that we can either observe the voltage at the drain or the voltage at the source. And since gate to source voltage is the control knob, we should be able to adjust the current adequately by either changing the gate voltage or the source voltage. So 2 cross 2, there are four possible combinations of coming up with distinct type of biases, a distinct type of biasing schemes. Out of these four, we have discussed two. One is the one that you already see in the screen, and the other was essentially this. You simply connect the current source to the source of the transistor, and everything gets auto-adjusted. And why does it work? It works because with respect, I mean, if you simply follow the argument, if the current source I naught, for example, in this case, is higher than IDS, right? That is, the transistor is trying to, the amount of current, let's assume that at startup, the VGS of the transistor is not high enough to provide the requisite amount of current I naught, which means IDS is smaller than I naught, which means if I concentrate on that node VS, the source node, I'm pulling out more charges out of that node than we are pushing in, which means VS will go down. If VS goes down, naturally the transistor action now kicks in the sense that your VGS is starting to increase, which means IDS will start increasing. And this balancing will go on till the time IDS becomes equal to I naught, right? And the voltage and this configuration will eventually settle to that value of VS for which you have IDS to be exactly equal to I naught. Okay, so that was essentially the principle. That was the thought process, and we did some calculations, and we figured out that what is the minimum VGQ required, and we saw other ways of biasing, right? We put in now extra transistors to see how can we bias with a single current source if you have to bias multiple of these configurations and so on, and that's how the design eventually proceeds. So what I would like to do is focus on the other two ways of biasing the transistor. Let's focus on the third one, right? So we'll apply the current at the drain, and we'll observe the source voltage and correct the source voltage itself, right? So that's what we'll try to do. So let's focus on that. So by definition, what are we trying to do? We are saying that we have this transistor, will not touch the gate. So gate will be some bias voltage. What will be this requirement of the bias voltage, or the value of the bias voltage? We'll figure out later. But the requirement is, as of now, the current source will be applied to the drain, right? And we'll have to do something to the source. right? So this is the third in the list. That is, we apply current source at the drain. That is, observe the drain voltage and tweak the source voltage. So nothing is connected to the source as of now. We have to do something to the source to ensure that this current I naught exactly equals this IDS. Obviously, under the condition that the transistor is in saturation. The way we have connected it, it will always be equal, but under the condition that the transistor will be in saturation. Okay, so again, let's assume that there is a small capacitor, helps in visualizing what is happening to the node. So now let's walk through the same arguments, right? So let's assume that if IDS is less than I naught, right? If IDS is less than I naught, what's going to happen to the drain voltage? So drain voltage is going to increase. So what information are you, if you observe the drain voltage increasing, what information are we getting? We are getting this information effectively, that IDS is less than I naught, right? Simply by observing the drain voltage. So I am flipping the argument on its head. So I'm saying if IDS is less than I naught, then VD increases, right? If I can flip the argument on its head and say that if VD increases, then we know that IDS is less than I naught, right? Same argument expressed in a different language. Okay, so we know we know what is happening. We need to correct it. So what should I do? I have to do something to the source. That's what we want to do by definition. So what should I do to the source to ensure that IDS becomes closer to I naught? We should decrease source, right? We agree? We should decrease source. So essentially then corrective action is what? Corrective action, decrease VS. A source voltage, let me write source voltage. Okay. Okay. So now you see this is slightly different from whatever we have done till now. So in the first case, when we were tweaking the gate, right? In the first topology, when we were applying current at the drain and we were tweaking the gate, this requirement was in the same direction. If the drain voltage increased, we needed to increase the gate voltage, right? So the obvious thing to do to try out was simply connect the drain and the gate, right? In the case where we had the I naught connected to the source and we wanted to only tweak the source voltage, it was auto-adjusting. We didn't, even better, we didn't have to do anything. It was transistor was going in the direction that we wanted to. But here it looks like we have to do something else. Because if the drain voltage is increasing, we have to decrease the source voltage. That's what the requirement seems like, right? So let's take a leap of faith and say that till now, whatever topologies we have learned, right? Forget about this one. Whatever topologies we have learned, which topology gives you an inversion between one node to another? Inversion of voltage. So that's what we need, right? Looks like, right? If VD increases, I have to decrease some other voltage. So think of it in this way. Let's say I have two nodes. Let's say this is V1, V2. I need to connect something between the two nodes such a way that if this increases, this decreases. What are you going to do? Forget about magnitude and all, just sign. Among all the topologies that we have learned, which topologies are most suited to do this? Yeah, right. So it's like common source amplifier does that, right? Our simple common source amplifier does that. If one terminal increases, the other decreases. So let's say this is V1, this is V2. If this increases, this decreases. Right? Seen this? Okay. So all we have to do is to maybe apply a common source amplifier type of topology between VD and VS. Correct? So if VD, what is the requirement again? If this guy increases, I have to decrease this. And it has to be done automatically, obviously, right? So what I propose is to do this. Apply some inversion stage, having some gain. I don't know what the gain is. Some inversion stage which gives you, some stage which gives you inversion of voltage between VD and this node. It's a VS. Okay. And we know that this is a common source amplifier. A common source amplifier can do that. Okay. So let's use a common source amplifier there. So this is an input stage. Again, I don't know whether this will get biased or not. I'm just connecting it up. If biasing is not proper, we'll add additional contraptions for biasing. This is just, we're trying to synthesize something and then see whether an analysis is necessary. Okay. So this increases, this decreases, I know. I can simply try out connecting these two directly. Right? Okay. So simply connecting these two directly might work, might not work. Now the analysis will kick in, right? We'll have to figure out whether connecting the topology in the way we have shown here will work or not. Okay. So this should remind you of something that you have done in one of the problem sets, right? Okay. So now let's forget about the CP for the time being because we are doing quiescent. Okay. So now if M1, this is M2. Now to ensure that again, for all these cases, we have to ensure that M1 and M2, all transistors are in saturation because this common source amplifier also works when things are in saturation. Right? And we wanted to ensure that M1 is also in saturation. Okay. So before doing the analysis, let's do a sanity check and see whether indeed this is a loop. We have to ensure that indeed the loop action works and it ensures that if VD increases, the current adjusts itself and brings VD to whatever value it is supposed to be. Okay. So what I'm essentially saying is that the arguments that we had laid out earlier was essentially to ensure that if the transistor goes out of saturation, the contraption that we add should be able to bring it back to saturation, right? In other way of saying the same thing is, if let's say for some reason VD increases or VD decreases, let's say VD decreases, it's easier to visualize what happens if VD decreases. If VD decreases, the whatever contraption that we have connected should be able to move the voltage at the drain voltage to the other direction, right? So we have just do a sanity check of whether that is happening. Then we'll do the calculation. Okay. So let's assume VD decreases. If VD decreases, the gate voltage of M2 decreases. If gate voltage of M2 decreases, what can you comment on VS? VS will increase because if M2 decreases, what happens to this current? This current decreases. This current decreases, which means VS will increase. VS will increase. If VS increases, what is happening to VD? Okay, think in terms of current. Yeah, VD increases, right? Think in terms of current. So let's only visualize current. If the gate voltage decreases, this current will decrease, right? If this current decreases, this current is the same as this current through M2. So essentially now I am pulling out more current than I'm pushing in, which means the drain voltage will increase. So there is a corrective action. And these two will balance out only when things are, this circuit will eventually settle to the value when these two balances out. Okay. So the next thing is to assume that it has balanced out, right? And we are doing the quiescent calculation to see whether under the condition that it has balanced out, whether the transistors are in saturation or not. Okay. Okay. So now let's do the calculation under the assumption that circuit has balanced out. Okay. So now, since you have already done this as one of the assignments, so what do you think should be the strategy to ensure that M1 is in saturation? Let's say VB1 is some value that we have decided. Let's assume some values. Let's say VB1 is 2 volt. And threshold voltage is 0.5 volt. I don't know this is going to work or not, but let's assume this. If it doesn't work, we can always change. So VB1 is 2 volt. What is the minimum VD or VD1, I should say in this case? What is the minimum VD1 that is required to ensure M1 is in saturation? 1.5. Okay. By the way, does VS play a role? No, right? Ultimately, it's the difference between the drain and the gate voltages. Okay. So VD1, this has to be greater than 1.5 volt. Okay. So this is the same as the gate of M2. So this has to be greater than 1.5 volt. So I want M2 to also be in saturation. So which voltage should I look for? Vs. So this needs to be greater than what? 1 volt. This needs to be greater than 1 volt, right? So this is needs to be. Okay. So now, if this is greater than 1 volt, so what is how do I know whether it is greater than 1 volt or not? So essentially, what I'm asking is that who is setting Vs then? Because Vs is connected to the source of M1 and drain of M2. Yes. Why not M2? Current is fixed, right? So VGS of M1 is setting the Vs because gate voltage is fixed, current is fixed. Only the source voltage can go up and down. So essentially, Vs is what? So then I have to focus my attention to whatever is the condition on M1. So Vs is essentially VB1 minus the VGS of M1. Now VGS of M1 is how much? This is equal to the threshold voltage plus the overdrive. So overdrive is 2I0 UNC ox W over L, right? So now you do your calculation, like VB1 is 2 volt, VTH is 0.5 volt, this is 1.5. Is that correct? 2.5, yeah, 1.5 minus overdrive. VB1, we chose 2 volt to start off. No, we didn't take 1.5, right? VB1 is this 2 volt, right? Okay. So this is 2I0 by mu NC ox W over L. Now, see, I haven't told you what I0 is. I haven't told you what W by L is, right? So now maybe you wanted to bias 1 milliamp of current or 100 microamp of current, whatever, that will be given. So that's not in your control. So what is in your control? W by L is in your control, right? So for some reason, you did this calculation and you found that Vs is not high enough, right? Vs is, let's say, 0.9 volt. You did this math and you found that Vs is 0.9 volt. Okay, so clearly, which transistor has a problem then? No, M1 is in saturation, right? M2 will have a problem, right? So M2 has a problem. If M2 has a problem, then I need to get M2 out of saturation. So what should I do? Essentially, what I'm asking is that what should I do to lift Vs, right? Getting M2 out of saturation means what should I do to lift the source voltage? Increase W by L of M1, right? Let's say current you cannot reduce. Let's say current, yeah, but that sometimes is an option, right? So, but let's say current you cannot reduce because often these type of circuits are required because you want certain value of GM, right? For that you fix the current, right? So then you don't want to go back and change the current, right? If possible, change something else send something else which is which you have added to bias the circuit. So essentially our goal is to bias M1 with a current of I0. We have added M2. So if something needs to change, we probably will have to see what can be done. If nothing can be changed, then we can play around with VB1, we can play around with I0. Those are secondary options, but those are nevertheless design knobs. Okay. Okay, fine. So let's say, let's think about this in this way also. So let me redraw this network. So let's say, let's take his point that let's say we can change I0. Okay, so VD1, VS1. So under Poisson condition, we find that maybe for certain value of I0, VD1 is at this value and VS1 is at this value. Let's say this is VD1Q, this is VS1Q. Okay. So now let's say I play around with this and let's assume the transistor is in saturation for now. If I increase I0, right? I want to increase I0, that is I'm going this side. What can you comment? What's going to happen to VD1 and what's going to happen to VS1? Okay, VD1 increases and what's going to happen to VS1? Right, so if VD1, in this case, VD1 will increase and VS1 is going to decrease. Okay, so now, if I keep on increasing I0, which transistor is, again, let me name M1, M2, which transistor is likely to go out of saturation? M2, right? And let's do the opposite. If I keep on decreasing I0, right? If I decrease I0, this guy will go this way, this guy will go this way. Then obviously M1 is likely to go out of saturation, right? So you have to have a balancing act, essentially, right? So to ensure that M1 or M2 remain in saturation. Now, how much margin you want? You obviously don't want it to be exactly at the edge. How much margin you want depends upon those things, right? How much input swing you are processing and all those things, right? So how much, what if there is a input connected somewhere, then you have to figure out how much each voltage can change, and under the condition that the input has changed maximum, right, from its quiescent state, you have to then see, you bias it in such a way that all transistors remain in saturation. Okay, that's essentially the mantra for going about any circuit design. Okay, any questions? So what I would recommend is, just like we are doing for this circuit, any circuit that you see from here on, do this exercise yourself. Even if I don't explicitly do it in the class, even if the assignment doesn't explicitly ask you this is a good exercise to do. What if? Ask yourself, what if? What if this changes, right? Now, what are the things that can change? What if I0 can change? What if W by L of M1 changes? What if W by L of M2 changes? What if the bias voltage VB1 changes? Which direction your circuit is moving? So as long as if you answer that question to yourself, you'll be good. I mean, that's what essentially circuit design is. Maths is something we have to do because we have to do some calculations to give grades, right? So, I mean, otherwise, when you are actually doing design, those of you who will be going into circuit design, you will see you'll probably not even do maths after some time. You'll just see that whatever you do in your labs, you will do that. You don't sit and do the maths in lab, right? When you are trying to bias circuits or get something. You just see, if I change the knob this way, which side the output is moving, right? So that's all we do. But for that, when you have multiple transistor circuit, you need to understand who sets what. Because if you ultimately, when everything is connected, you change one thing, n different variables are going to change. Eventually, everything is going to change. You need to figure out which is the dominant variable which affects the functionality. And that comes from understanding the major knobs. Okay, so that's what I am trying to inculcate here. Okay, any questions on this? Okay, so let's say that I mean, since you have done this in your in one of the question sets, the next thing should be obvious. So let's say I want to apply, I make it a common source amplifier where M1 is the main transistor. Then I can add the input here, and when I add this input here, does not mean that I am only adding it in series. We know how to add the inputs, right? You put a resistor divider, put a capacitor, couple it, decouple it, and apply. So same thing will be applying here. And we want to, let's say, take the output from VD1. Okay. So what I'm essentially saying is there is probably a resistor RL, which is connected. I want to connect this RL to VD1, because a common source amplifier eventually looks like this, right? You apply something at the gate, you take the output from the drain. So if I simply connect RL to VD1, will it work? No, right? So what is the solution? Put a capacitor, right? So you put a capacitor here, say C2. But will, if I simply connect it like this, is it going to work? So now think in terms of incremental domain, right? So this voltage, let's say, is changing. What I'm essentially asking is, will this current change? Because if that current doesn't change, I don't have any incremental current. If I don't have any incremental current, nothing can flow into RL, right? So the question that I'm asking is, if VI changes in the topology that I have shown, do you think IDS1 is going to change? Why do you think it's going to change? Yes, it will be, but VG is VI. What about VS? So let me make it simpler. Let's not connect this up. Let's only have it like this. So again, think in this way, right? What is the circuit doing? Whatever we have connected up, the circuit is trying to balance the current in M1, M2 to ensure that the current is always equal to I0, right? So the current cannot change. It's a constant current bias. Correct? So whatever I do to VI, current will not change, isn't it? So what will change? Something else will change to ensure, I mean, gate is increasing, current will not change. So what can change? VS will increase, right? So essentially VS1 will follow VI to ensure that the current doesn't change. But now this is good as far as biasing is concerned. But when you want to ensure that we get a common source type of operation going, then this is not particularly good. We want the incremental current to change. Correct? So essentially we don't want the quiescent current to be dependent on all those things. I mean, all those variables, but we want the quiescent current to be dependent on the input. Sorry, we want the incremental current to be dependent on the input, not the quiescent current, right? So now, can you suggest a solution? So essentially, the problem statement becomes, under the quiescent, this is fine. Under quiescent state, this will work as long as M1, M2 in saturation. But when I'm talking about incremental, when this guy changes, I want IDS1, the current through M1, to be also changing like GM times VI, right? Where VI is the gate voltage. When I'm saying that the current should change, this is expected that this should be like GM1 times VI, right? What am I inherently saying the source voltage should do? It should be grounded incrementally. Correct? So what can we do to ensure that VS1 is grounded incrementally? put a capacitor to any constant voltage, ground, for example, right? So let's say I call it C1, right? So if C1 is infinitely large, for any incremental current, the IDS one is going to flow directly through this, but the incremental current is going to flow into the capacitor, which gives you a, capacitor impedance will be shorted if C is infinitely large. Okay, so now if this is the case, so now if I connect the RL to the capacitor, right? So then you see this incremental current has a place to move through this output capacitor and RL and close the loop. Okay, so now you can have the voltage across RL, which will behave like a the relationship between VI and the voltage across RL will be that of a common source amplifier, which is GM times VI. Because in the incremental sense, M2 really doesn't affect VS1, right? Because VS1 is being shorted by the capacitor. Make sense? Doesn't make sense? Okay, so let me clean up the circuit a bit. So are we comfortable with the quiescent part? Okay, fine. If we are comfortable with the quiescent part, the next part should be quite simple. So in incremental sense, what we want? We want this to be, this is VI. So this should be GM1 times VI, and this should go into RL. This should be the V0. This is what we want. Correct? So, but we see that M1, the current through M1, the incremental current through M1 is GM1 times VI minus VS. Why we need that VS1 previously grounded? Why do we need that VS1 as grounded? Yeah, so let's say it is not grounded, right? So that's what. So let's say it is not grounded. So this incremental current will be GM1 times VI minus VS1. Correct? So, but in the incremental sense, what do we want? We want GM1 times VI. Right? So right now, if I don't connect the capacitor, if this capacitor is not there, then the current through the incremental current through M1 is not GM1 times VI. It's GM1 times VI minus the source voltage. If I want M1 to behave like a common source amplifier, then in the incremental sense, the source would be grounded. If C1 is not there, there is no incremental current, right? So that's it. That was good because that was itself helping us bias, right? So let's say C1 is not there, and for some reason this voltage increased, right? Maybe V1 is, this biasing is coming from a previous stage, that voltage increased. So this voltage increased. In the absence of C1, in the absence of all the incremental stuff we have added, that we have added up, what's going to happen to VS1? It is going to increase, right? Because it's constant current bias, right? So VGS of M1 is going to keep whatever it was supposed to be. So gate voltage increases, source voltage also increases. So that is good for quiescent biasing, but that is not good for getting gain. Incremental gain, that is not good, because for incremental gain, I want that gap of VGS1 to open up, because unless I move VGS1, I will not get incremental current. So now gate is moving because it is getting driven by something else. I don't want the source to move incrementally, right? So essentially I have to incrementally ground the source. So what is the only way we know how to incrementally ground anything? Put an infinitely large capacitor, right? So that's all we are doing. We are putting an infinitely large capacitor. So putting a capacitor has double benefits. We don't have to bother about biasing because it doesn't move the biasing voltage, no DC current, but it can potentially give you a very low impedance if you size it properly, right? If you size it large enough, at any non-zero frequency, right? So if C1 is kind of shorted, then let's look at the incremental picture. In the incremental picture, then yes, we'll do. If I'm only concentrating on M1 for the time being. Okay. So question?
But if Vs is not zero, like if it is not shorted, even then we can solve the incremental.
Sure.
Even then we can get some VO by Vs.
Yeah, you can get, but what will that be?
Would be some ratio.
Yeah, but if will it be zero or non-zero? How will it be non-zero? So let's say we have this, right?
No, this is connected.
Okay. The other part is connected. Yeah. Yes, you will get something, but it will not be GM1 times VR, right?
It will be some ratio.
Something. It will be less than what you want. Correct. Right?
Or the maximum condition.
Yeah. Correct. Yeah. So ultimately, the whole point is, I mean, we would like to ensure that this behaves like a common source amplifier. His point is, even if I don't short the VS1, right? So there seems to be if an incremental current flows, there seems to be a loop for the incremental, which is correct, which I agree, but it is not the maximum that we can get. Okay, so to get whatever the maximum that we can possibly get, we have to short VS1 incrementally. So that is through a capacitor, and capacitor is kind of, I mean, it's one of those things that you can keep on adding, assuming it's not like infinitely large, and you size it in such a way that the capacitor is, I mean, you find out the time constant associated with the capacitor, and then go ahead and then see whether this time constant is large enough with respect to 1 over omega naught. If that is true, then it's shorted. Okay. Okay. So now let me come back to his point. His point was, if this guy moves, so by the way, the direction will be opposite. If this is this way, this should move the other way because there is an inversion. So this has the voltage of M2, gate of M2 is also moving, right? Incrementally, the gate of M2 is also moving, which means the current through M2 is also going to change, right? Agreed. It is going to change. But is it going to affect RL, I mean, the voltage across RL? Where will that incremental current of M2 go into? Through C1, right? So incremental current of M2 will essentially be circulating between this drain and the source. Okay. So since I mean, only purpose of M2 was to give the bias. It was not supposed to affect our main operation. So C1 also helps in doing that. Okay. Okay. Any other questions regarding this? So we'll come back to the circuit later on. This also has a very important application. We are not yet at that stage to appreciate that, but in a couple of classes, we'll come back to this circuit. Okay, fine. So this is, I mean, one of the ways of biasing your transistor with this ideology that you observe whatever, you connect the current source at the drain, observe the drain voltage and tweak the source voltage. And this we have done using an NMOS amplifier. M2 is an NMOS transistor. What I would request you to do is go back today after class and follow the same argument, and then put the common source amplifier, the extra transistor that we have put, right? The M2 that you have put is an NMOS transistor. Do the same thing using M2 to be a PMOS transistor, right? So again, what I'm asking you to do is this. So we did this, right? Where this guy is a NMOS common source stage, which was M2. What I want you to do is make this a PMOS common source stage, right? and argue with yourself. If you connect it using a PMOS, what needs to be done, what extra things needs to be added, and so on, right? So obviously you see that if you simply connect it, then probably you will have some problem. So argue with yourself what else needs to be connected. We can talk about it later. Okay. Okay. So before we end, so let me also give you a primer for the last thing that remains, which is this part. So apply current source or pull current out of the source and observe the drain voltage, but do the corrective action at the gate, right? Yeah. No. So I think okay. Yeah, this is fine. Yeah, apply the. So I think there is a mistake there, but anyhow, let's correct it here itself. So what I am essentially saying is that so we have done two topologies where we have connected the current at the drain, and we did current source at the drain, and we did corrective actions, right? We applied the current at the drain, tweak the gate voltage. We applied the current at the drain, tweak the source voltage. The third one that we did was we applied the current source at the source, and we saw that automatically the source gets biased. The last one that is remaining is apply the current source at the source and tweak the gate voltage. Right? That's what we would like to do. So by definition, we are applying the current sink in this case because we're pulling out current sink or current source. I mean, doesn't matter for the context at the source, and we would like to do something to the gate. Okay, so we'll observe the source voltage and do something to the gate. Okay, so let's argue in the same lines that we were arguing earlier. So let's say I observed the VS, the source voltage of M1, and we observed that VS1 is, let's say, increasing. Okay, so VS1 is increasing. So what is the conclusion with regards to the currents? VS1 increasing means IDS1 is higher than I0, right? So conclusion is, this implies IDS1 is greater than I0. So the corrective action required is, what should I do to the corrective action with regards to VGS? We need to decrease VGS, right? So corrective action is decrease VGS. We don't want to touch the source because we want to touch the gate. That's what we are essentially saying, which means, what should I do to the gate? We should decrease VGS, right? So it implies decrease VG. So if this increases, we should decrease VG. Okay. So again, same logic, right? There is an inversion associated. Correct? There's an inversion associated between the source and the gate voltage. Yes. Yeah, right. So it's self-correcting if you keep the gate voltage constant, right? So that was the topology that we did in the previous class, right? So what we are now saying is that in that topology, we didn't bother about the gate voltage. The gate voltage was kept constant. Now what we are saying is that, can we do something to the gate voltage, right? To maybe make it a better version, right? We don't want to, even though it is self-correcting, what I am trying to get at here is that, can we do something better to connect to get the gate voltage move in the direction that we also want? Okay, so again, we have to put something between these guys. What is the we have to put a block. Now tell me, I mean, when we are putting a block, the very basic thing, which is the input, which is the output, right? So let's say this is you have to put some block here. So tell me in this block whether this voltage VS1 will be the input or VG will be the input. VS1 will be the input, right? So okay. So and what should be the characteristics of the block with respect to the sign? It should have inversion, right? And what is the only thing that we know which gives inversion? Common source amplifier. So what we will do? We put a common source amplifier. So now if the way we did in the last case, we simply connected, right? In the previous case, we put a common source amplifier and simply connected the two nodes. But do you think if I do that here, it's going to work? So again, I mean, what I meant was here, we applied the common source amplifier and simply connected the output, the drain of M2 to the source of M1. But if I try to do that here like this, is it going to work? No, it's not going to work. Why not? There is no current. Exactly, there is no current. This current is zero. So we have to ensure that this, if I call this M2, it has some current, right? So how do I bias a common source amplifier? I mean, simple bias. I do this. So I call this RD. Okay. So if I do this, then probably there can be, I haven't yet established the fact that the circuit is going to work, right? All I have done is to give okay, so let me take a step back before I connect RD. So if I do this VDD, right? If I do this VDD, will M2 get current? It's going to get current. But in this case, the gate voltage of M1 becomes fixed. It's not moving, right? We wanted an inversion between VS1 and VG. The inversion is not happening because VDD is holding that gate voltage. Okay. So we want M2 to have the requisite voltage, this VD2, let's say. This VD2 has to be of some value, but it should not be held to that value because of the requirement of M1. So we can achieve that by simply not connecting VD2 to VDD, but we can connect VD2 to VDD through another resistor. Okay. So now once we do this, we can go ahead and do our calculations and see whether M1 and M2 remain in saturation or not. So those analyses we can do separately. Okay. But once we connect it up, it's always good to do a sanity check and see what happens if IDS1, let's say, is more than I0. Now let's do the same thought experiment. Let's say IDS1 is more than I0. Then what's going to happen to VS1? That is the gate of M2. This is going to increase. If this is increasing, what's going to happen to the current through M2? It will increase. What's going to happen to this voltage, VD2? It is going to decrease, right? Because current through M2 increases. So you are going to have more drop across RD2. The voltage at the gate of M1 is going to decrease. If voltage of the M1 is decreasing, what's going to happen to IDS1? It's going to decrease, right? And you see that is a double effect now, because source is increasing and gate is decreasing, right? So if you simply connect I0 to M1 in the topology that we had done in the previous class, we had only had one effect, right? The source was auto adjusting. In this case, the source is adjusting, plus it is forcing the gate voltage to also adjust. So in a certain way, this is a better topology because there are two corrective actions. Okay. Okay. So we'll stop here. We'll see that. I mean, if you open up textbooks, you will see some of these architectures are quite commonplace, right? You will start recognizing these architectures in about another week or so if you open up some of the standard circuit design textbooks. What I wanted to give you through this argument is there is a method behind how people come up with these architectures. It's not like today I want to make something with two transistors, I connect it up in a certain way and let's see what happens. There is always a method behind the thought that goes inside designing something. What I wanted you to appreciate is what the thought is. Once you understand what are the knobs, right? So once you put on a designer's hat, you understand what are the knobs. Once you know what are the knobs, right, which is the dominant variable, which if I change I naught, what changes, if I change W by L, what changes, then calculation is easy. There is only one equation in the entire course, effectively, right? So you put the equations and you get the answers, but you need to know what is the cause, what is the effect. Okay. Okay. Thank you.